All right, welcome to our first edition of the Sutro Team Spotlight. We're going to be trying something new today and actually interviewing people around the company at Sutro and just kind of seeing what they work on, what exactly the Sutro technology is, why they joined Sutro. And so for all of you out there that don't know what Sutro is a robot that floats inside of your swimming pool or spa. And we have an application on iOS or Android that tells you exactly what chemicals to put in and when. It's a pretty complex piece of robotics, and so throughout these next few sessions, you'll hear from our mechanical engineer, our chemical engineers, project managers, software development, and so we'll kind of go through the full gamut and really, see what's under the hood at Sutro. My name is Ravi Kkurani. I'm the CEO and founder of Sutro, and today we have actually one of our first employees, Alex Valeyev. So I won't steal too much of your thunder here. Why don't you go ahead and introduce yourself, Alex?
Sure. As Ravi had said, I'm Alex. I am a mechanical engineer for Sutro. I started at Sutro, I think it was like 6 years ago, maybe a little bit more, really early on when the company started. We were still trying to figure out how to make the technology work at the time. I joined as an intern at the beginning. I think we had a team of maybe 4 people there at the time. I joined Sutro initially because it seemed like an interesting engineering challenge, and I was trying to get, a bunch more experience. As I explained to Ravi, I think during one of our interviews early on, the way I kind of look at, engineering careers overall is you're building up your toolbox of stuff that you can kind of reach into and use to solve problems as you work through different challenges that come up in your career. And so I had a bit of experience in like one kind of pillar of engineering and around, prototype manufacturing and kind of one-off stuff. And I really wanted to get into something that was going to be a different discipline. Dealing with fluids is something that I hadn't really worked with before that. And then just looking at something that's going to go into kind of a mass production, which is a whole different beast than it is to make a one-off proof of concept or something like that. So that was really kind of what brought me in.
Awesome. Yeah, and I think we're going to go a little bit into detail on kind of the mass production side of things as well as the fluidics. So I'll reserve questions for that later on in the show. When can you kind of give like a high level to the audience of what you do at Sutro? Like what is the day in the life of Alex look like?
It depends, I guess, a lot on what we have going on and what part of what phase of development and or production we're in. I've found that over the years I have worn many hats at Sutro, primarily in the mechanical engineering side of things. A lot of the work that I'm doing is around coming up with, some novel solution, or at least kind of adapting existing solutions to fix a problem or challenge that we're facing. Everything from, how do I make this product cost effective, right? Bring the costs down enough to where someone can buy it. Because basically what we're trying to do is take what is like laboratory equipment that costs like thousands of dollars for a lab bench and is pretty expensive to keep operational in terms of all the consumables, and turn it into something that a customer can use, can afford to buy on like a consumer level, and can then also use it without it having to be a lab tech, right? And so a lot of the challenges kind of came from that, of like automating what is normally a hands-on process, which is kind of what falls into like my area of responsibilities, as well as figuring out ways to take something that like you can buy off the shelf, like a valve or something for a couple of $100s because it's a precision component. And how do I make it so that we can like mass produce this thing for 1/10 the cost, so that it can be in a consumer's hands without breaking the bank for them. So on the engineering side, that's a lot of what I'm doing, and have kind of transitioned more into also tracking mass production, something that I didn't have a ton of experience with before this, and been learning via steep learning curve on all of this of how to take something that we got to work on like 5, 10, 20 pieces and then say, okay, now let's do like 10, 15,000 of them, and they all have to work and they all have to be the same. So that comes with a whole new host of challenges.
So let's actually double click a little bit into the technology itself, right? I think for the audience, I'm going to kind of go into two different scenarios here. One is kind of double clicking into the technology itself. We're going to talk about kind of the microfluidic chip that Alex actually helped invent, how it works. And then I think what will be really actually interesting is, you've touched on this a few times around the mass production side of it. What does that supply chain even look like, right? Like, people will get a Sutro to their doorstep. How does that even happen? And so let's start with the microfluidic side first.
Sure. Yeah. So I think the easiest way is to kind of explain how the microfluidics works is to start at what we were trying to replicate. I think a lot of our overall kind of ethos to how we were building this product is take something that exists and either make it more accessible and cheaper, or automate the process and shrink it down as much as you can. So in the name of in the cartridge, that's kind of the latter part of that ethos, was to shrink it down, make it repeatable. So the easiest way to explain it is, you know, when a normal way that somebody would test their pool using, you know, not electric probes or anything, but actual chemistry, would be to buy a test kit. And then they would take that test kit and, you know, you'll follow the instructions. You scoop up, you know, 25 milliliters of water, and then you pour in a number of drops of the first reagent, stir it up, pour in a couple more drops of another reagent, stir it up again, and then you look at what the color is of that mixture that you've just made, and you reference that against, you know, a color chart that is on that little test vessel that comes with the kit, and you say, okay, this pink looks like that pink. And so that pink translates to, you know, 7.6 on the pH scale. And so now I know that my water is 7.6. So we were thinking, okay, well, what's the best way to basically replicate that process, and then also not have to carry like buckets of reagents in order to conduct like 100 tests or something like that. How do we fit this into a pool where it's not something the size of like a refrigerator that you're just dumping in your pool to measure the chemistry? And so what we basically did was we took that reaction chamber that became like the anchor point, that little volume, we shrank it down. So instead of 25 milliliters, we do 200 microliters. So a little bit less than, what is that, 1/100th of the volume. And then we just took everything else that goes with that process. We built a little flow chart of like, hey, you take the sample, add reagent, mix, add more reagent, mix, look at the color. And so we basically did that, and then shrank all of that stuff down and tried to fit it all into a nicely contained vessel that can be run autonomously, and we can, you know, ship it to a customer. They just put it into the device. Maybe an easy way to do this would be to actually show you the drawings that we use for production. So I can share my screen here, and we can actually take a bit of a deeper dive into the cartridge.
That'd be great. And I think in the meantime, I'm going to go ahead and actually grab one of the samples that we have here too, so I could just show everybody zooming out actually what it looks like.
So yeah, here we are looking into and kind of through our test cartridge, basically hidden some of the outer covering parts so we can kind of look inside and see how everything works. So basically, of all the tests that our device does, it requires a total of 5 different reagents to conduct all of the different tests. That basically allows us to do 3 different chemistries, pH, TA, and FCL. And so when we look into this, this is the actual microfluidic chip, is this piece here. And so when we look at the microfluidic chip where all the magic happens, you can see there are 3 volumes here. And these are the 3, what we call flow cells. These are the test volumes where we basically pull in water samples, and then we inject reagents in, mix them up, and then do a light reading. And so inside of here, we have basically 5 syringes filled with the reagents. And when I was talking about scaling down proportionally the volumes of taking that test, you know, when I said we basically scaled everything down by 100x. So when you think about that, the real challenge there becomes, how do you scale down 5 drops of that reagent that you just dropped in from a bottle into your test kit? How do you scale that down by 100 times? Like, what is the volume when that happens, right? And so for most of these tests, the volume that we're pushing in is actually 10 microliters. That's like 1/5 of a droplet, I believe. And so we have to get that pretty precise. We have about like a 10% plus or minus margin on that volume for the reading to be accurate. And so we have to go, anywhere between 9 and 11 microliters is kind of the tolerance that we have of what has to go into the flow cell in order to actually read chemistry and not get kind of useless data. And so the trickiest part was basically figuring out, how do we get that precise, and how do we keep our reagents that we're not using yet, right? We want to have like 100 tests inside of this cartridge. So when we take one test, we can't just contaminate and ruin all of our reagents. So we have to keep them separated from where that reaction is happening. And so that's where we have these check valves that we designed. For anybody that's listening that is kind of an engineering nerd and has some mechanical experience, these are technically more bidirectional valve that is heavily biased in one direction rather than a true check valve. That way we don't get called out in the comments. But basically what happens is, when we go to take a test, we've got these syringes here full of reagent. Inside of the unit, we can take a look at that a little bit later. We've got stepper motors on a lead screw that then push forward a pin that pushes the plunger. We basically still have a plunger in here like you would in a regular syringe, but we've just like lopped off most of that thing, and it only kept the seal and a little bit of the body of that plunger, and then the rest of that has been discarded in production. And so then that pin goes inside of this syringe, and it advances that plunger forward and pushes in a very precise small volume. And so that volume then goes through one of these little channels, these what I like to call the banana channels, and then they go into this volume here, which is basically the body of our check valve, or our bidirectional valve. Once we reach a high enough pressure, if we look at it kind of at a side angle, you'll see that the tips of these conical features stick out a little bit beyond kind of the rest of the flat face or the tops of these ridges. And so we basically clamp down a piece of silicone across the whole thing. And what happens is we're basically making like a little tent. We've got that little conical feature in the middle, and it raises the center of the tent, but that rubber is basically tight up against that plastic. And so then what happens is, as we keep pushing on that syringe, the fluid in the reagent pushes that pressure to lift the rubber a little bit, and then it goes through this central hole, and it goes, you can see the hole on the other side. We have 2 valves for this test, and it basically comes into here, into this volume where we've already filled it up with water. And so some of the challenges were, as we were prototyping, all of these features are super, super tiny. Like the hole that's going through here is only slightly larger than the diameter of a human hair. And so how do we mold those parts? How do we manufacture those? And then also when you're looking at, how do I separate all of my fresh, untouched reagents from the water that might contaminate them? You start to get into like this real microscopic level of things where the surface finish, like how glossy that plastic is, has an impact about how well it seals against the rubber when it's on top of there. And those are some of the challenges that we were dealing with as we were building out and designing these and working on the prototypes. Beyond that, we have a mixing ball that lives inside of here. We have this like little divot in this chamber. And so the mixing ball will rest down here. And then we have some magnets on the outside of the cartridge that will oscillate up and down and move this mixing ball up and down inside of here. And that will stir up kind of that mixture of reagents and water inside. And that'll allow us to get a full reaction. And then you'll see that here we have these like cutouts in the cartridge. Here we have in the monitor a piece of electronics here that goes, basically we have on one side of it LED light source. And so we shine a light, and then that light goes through this chamber where we have the reaction, and there's a sensor on the other side that basically looks at the color. And so what we do is we shine the light through just clean water, take a reading, and that gives us our baseline of like, this is what clear looks like to the sensor. And then when we add the reagents, mix everything up, we shine the light through and take another reading to see what colors now the sensor can see. And then the difference between what was just water and what was mixed will now tell us how much of every type of color we have. We basically break it down by wavelengths. And then the chemicals in the reagents will have reactions at certain wavelengths that we can pick up. And depending on the chemistry, you'll have either more or less of a certain wavelength that you can pick up with the sensor. And that will tell us what the chemistry concentration is. From there, our servers have some equations that will then calculate that out into a language that humans can understand, which is like a pH reading or FCL.
So it's so cool when you explain it that way, Alex, because I think the like audience, or somebody that even gets a Sutro just sees that pH rating, right? And like what you've explained here is basically a legitimate mechanical process of how somebody would test their pool with a little test kit that's been shrunk down to 1/100th of a regular test kit size. And that's awesome. Our lawyers will probably wonder, you gave a lot of information on this screen right now. Is it patented? Like, can somebody just take these designs and go ahead and like copy paste them and start selling Sutro? What does the patenting process look like here? And do we have protection on this?
Short answer, yeah, we do. Longer answer is we do, and we did patent the valve technology that we're using here. That's actually pretty novel. Hasn't really been used. One of the big advantages to this sort of check valve and this super tiny hole that's really hard to make in the plastic that we have to use here is that the volume of liquid, so like what we can control when we push reagents in is basically what volume goes up to this like interface between that rubber and plastic. Everything beyond that is basically on like diffusion and natural mixing. We can't like force it beyond that place. What the advantage of this valve is that it has what's called like a very small dead volume, a volume of area that like we can't control and is not going to really mix very well because it's not part of the rest of this reaction chamber. And so that's kind of the whole logic behind this check valve, and is unique to Sutro, is patented by Sutro. Apparently nobody else thought this was a great idea before, so came up with that one. And then besides that, I can give you the full details and like all the drawings for this thing. Making it actually work and dealing with all of the nuances that go into like how to mold these parts, how to control all of the quality around like making sure this was molded properly and testing it, that sort of stuff goes beyond what's covered in the patent and is required to actually make this work. You can probably mold this part, but to actually get it to take readings and make it work would be a separate challenge from just copying the drawings.
Yeah, definitely. Actually, that's a perfect segue. Let's go ahead and dive into, let me kind of show the audience out there that's watching on YouTube the actual device. Alex, if you want to kind of unshare your screen, I can zoom into this video.
Yeah.
Really quick. So this is the Sutro device right here. This thing's about the size of my forearm, and it floats inside of your swimming pool or spa. Kind of interesting little story here. This piece coming up was actually modeled off of the flux capacitor in Back to the Future when we were designing that. And that part that Alex actually just went into detail in is this cartridge right over here. So this is the part that you replace every single month. Alex, why don't you talk to us a little bit about kind of manufacturing this thing, right? People get this box, it shows up at their doorstep. What goes into actually getting this product made and it's showing up at somebody's doorstep?
Yeah, so a whole bunch of stuff went in. Basically, when we started to kind of look more seriously at like, all right, how are we going to mass produce this thing? We had already had most of the architecture set up, and we were already producing like samples for our testing internally and like some small quantity field testing that were being made. And so a big chunk of the problem or differences and challenges that came along with that was the change in manufacturing methods. I think, people who are in like product design and that sort of stuff will probably know what we're talking about here. But basically, when we go to make one of these things, when I'm prototyping something out, I'm not going to make an injection mold, which is how like most consumer products are made. At least lots and lots of them, most plastic stuff. When I'm doing that initially, I'm either like 3D printing parts, which we can get into as a whole separate thing of like surface finishes, and when you get down to this small level like of features, as well as dealing with fluids, it becomes a whole other ballgame. But for the most part, what we were using, especially for the fluidics, was we were machining these parts out. So we would start with a block of material and cut it away. So there are different requirements basically for these different manufacturing methods in terms of how the part is designed. So some of them overlap, but a lot of them are very different. So in the case of making prototypes, what goes into that is I start with like a block of material, then I have to cut that material away until I'm left with just the part that I want. So when I'm designing the part that I want, I will try and take into account how much material am I going to use, how long do I have to like cut this stuff up for to get the part that I want. And so I will tend to leave the designs big, blocky, leave a bunch of material in if it's not in the way, because then I can get to having this part done faster, because time is money, and the longer a part has to be machined to be made, the more expensive it's going to be. Irrespective of that, making parts this way is really expensive. Part that you could make for like the fluidic chip, for instance, making it by CNC and like cutting it as like one-offs, you're easily in the hundreds of dollars to make the part, especially if you've got tight tolerances like we do. I don't think we would have a very large group of people that would be into spending like $15,000 on a Sutro because of how much all the parts cost. So when we go to mass production, we got to switch everything over to injection molding, where we pay once for the tool, and it's a custom tool that just makes this one part. Pretty expensive to make the tool because it's made the same way that the prototype parts were. You cut away the material from a big block. But after you're done with that, at that point, you're just shooting molten plastic into that tool, and out comes your part. And you can do that repeatedly for like 100,000 times. And so that brings the cost of the parts that we're actually going to be able to offer to the customers, that brings that cost way down. There's a big change in your design thinking that happens when you go from I'm cutting away from a block to I'm shooting hot liquid plastic into this metal container and then cooling it and having my part. And so a lot of the work was basically, how do we take all of the parts that we've like meticulously designed as a proof of concept and now transfer all of the critical functions and dimensions and everything like that over to a different manufacturing process. So that was a big chunk of the work. Another big part of the work was when we were building our prototypes, we were using off-the-shelf electronics, stuff that we could, like a microcontroller, like an Arduino or the like, that we could then just, write some custom firmware on existing electronics, plug all the stuff that we've got, all our motors and all that stuff in, all our sensors and lights, and then run the prototype. And again, for a prototype, yeah, we'll spend a little bit extra on the like pre-made boards that somebody else already designs and builds and mass sells. But they've got a whole bunch of stuff on them that we don't utilize necessarily. Like maybe I'm only using 25% of the functionality that board is capable of, but I'm paying for all of it when I go and buy it. But for prototyping, that's fine, because that's the fastest way I can get to validating that this thing works. When we go into production, we basically like cut away all the fat. We don't need half of the functionality on this board. We don't need a bunch of like the indicator lights that are on the board for troubleshooting, because at that point we've got like a whole testing suite and stuff set up in production. And then from there, you basically do all of this electronic design to, again, bring down the cost to where it's now at a consumer level instead of like a company paying for R&D level.
So kind of quickly walk us through, you kind of just told us about how you move from prototype to mass production. Now that we are in mass production, just quickly walk us through like how many quality assurance checks do we have? When the unit arrives in the United States, what kind of happens at that point in time to literally trace the journey from this actual box that's being manufactured all the way to somebody's doorstep and then ending up at somebody's pool.
Sure. Yeah. So let's say, the design's finalized, all that is good to go. We have our processes set up, and I say, all right, let's start production. So once we hit the big button on that says go on it, for that, what happens is orders go out to a number of vendors that we have worked with that have all of this injection molding tooling, for instance. And so what will happen is they will start to do the production. On their end, there are, when we send the designs and all that stuff over to this vendor, there are like critical dimensions. So there are specific places on the part that I will say, from this like mounting hole to this mounting hole has to be a specific distance, because there are other parts that are counting on this being reliable distance in order for them to fit properly, right? Because I want other parts from somewhere else that I've sourced, where, a motor that I bought from a company that makes motors, it needs to always be able to mount in this part. And so we send a bunch of critical dimensions to them that they will inspect at the factory. And so typically the process there will work. They will buy raw materials. They will take samples of those, do an inspection test that the materials are what the vendor promised, that they're in the condition that was promised. They will do an initial inspection of all of the tooling, make sure it's like in good working order. They will fire off maybe 10, 20 initial parts. And then we'll do basically what's called like a first article inspection. So once those come off, they will do a very detailed, thorough inspection that like every one of those parts is exactly as was designed. And then from there, they will take those parts that have been approved once they meet all of the QC checks. They will mold, 100,000, however many parts that's necessary for our production run. Throughout that process, there are like critical places, like critical dimensions, that they will pull parts out as they're coming off of the production line and measure those and then put them back, as long as the measurements are good. And so we will work with that vendor to set standards of like every 100 parts, you should be pulling like 5 off and measuring those. And so we'll set standards, and then we will say, oh, if one of those 5 parts didn't meet that specification, A, you're going to throw that part out because it's no good. But B, that means that something is wrong with that batch that you just did. So you're going to pull out all of them and then check every single one, where we're counting on statistics to basically work out that if 5 random samples are good out of a batch, then and all of them are fine, then the rest of that batch should be fine. If one of them has a problem, well, that means maybe 20% of that whole batch has a problem. So now we have to take a closer look. Then they do like a final inspection and packing at that vendor, and then they will send it to our factory where we do the final assembly. When it shows up to our factory, we will do another inspection, basically just double checking the work of that vendor that we've worked with to say, okay, well, we have basically the same, they have outgoing quality control standards they have to meet as the products leave their facility. We have incoming quality control standards, so that when it shows up at our facility, we will check it again and say, yep, these same statistics work out. We've got the same numbers. We match what they sent out and what we received matches up. Good to go. We can use these parts in production. And that will work for basically all the components that we get, whether we make the part ourselves or whether we are buying it from somebody who like makes motors or something that's more standard. And then the same will go for all of our electronics are assembled in-house. And so the same will go for that process where we will put in the design. It runs through a mostly automated process to do all of the assembly. And when those first few parts come off, they get like a super deep review of like every single function, every component is tested, make sure that it's working within the specs that have been outlined. Then after that, we will also, again, in process quality control steps, where as stuff is coming off the line, we'll grab one every so often at a random interval and then test those to make sure that it's all still working out okay. Then we'll do the assembly steps, and then at each sub-assembly where like I'll assemble the top part of the unit where like 20, 30 components go together, and then another part of the component, and then those 2 sub-assemblies will mate together to like make the rest of the unit. Each one of those sub-assemblies is tested again. So if there's something out of spec, we'll like stop the line and start looking upstream of like, where did something go wrong? Do we improve a process, or do we add another check somewhere that like something got missed? And then once the whole product is assembled, we then also will do another. First, we will again pull out first articles. So like every step of this way, you basically, as soon as a process has been established and you run some number of parts through it, you do a first article inspection. You have this long detailed checklist of like, this has to be a certain way. Every piece has to be a certain way. And you will run through all of those checks. So like when the monitor is complete, it goes through what is basically we've built a test firmware. So it's like fully automated, hooks up to a computer via cable that flashes a test firmware onto it. And that basically will run the device through every function that it can possibly do. And then return that, hey, it like ran the pump and the pump sounded good. And like it put out the right volume, good to go. Like this subsystem has been checked. And we'll basically go through the whole unit that way. Then there is like a manual final like visual inspection by a human that will double check that everything that's been done autonomously so far looks good. Then we do like a final packing. Then that goes to the US and to our warehouse. And so that's generally the process. I think we have, probably like 20 to 30 different quality control checkpoints for basically every like component. And then inside of there's like 20 parameters for every one of those checkpoints to make sure that things are the way that they're intended to be.
So awesome. Yeah, I think actually listening to you say this, we should probably just like have a just kind of tracing the journey of how Sutro actually gets to your doorstep. I think that could be really cool as like a video in itself. Kind of two before we close up. In the kind of beginning, you had mentioned that we went through all this work to make sure that we miniaturized a regular test kit. Notably like pH probes and ORP probes. Walk the audience through kind of what experience you have with those probes and why we ended up going with a reagent technology.
Yeah, so when I first started out at Sutro, Sutro was in the process of basically closing out this like little pilot run that they were doing with pH and ORP probes. And we've used them a little bit in terms of in like laboratory comparison testing and that sort of thing. The biggest issue with the probes that we have found in our experience is there's just this constant drift and need to recalibrate the probes manually. That is just a factor of their like design. Basically, the way that the probes work is they will measure electrical potential that is due to chemicals in the water, like the chemistry, the pH and chlorine. Those will create basically there's a sensor inside of like a glass bulb, and then another sensor, like a little electrode on the outside of it. And so what those probes are doing is they're basically measuring what is the electrical potential between those two electrical probes that are on opposite sides of glass, where one is like a neutral and then the other one is in the water. It's if you've ever used a multimeter, it's not super different from measuring a battery, where one is ground, which would be the center of your probe. It reads your baseline, and then there's the other one, which is where you're like touching the positive terminal of something to determine the voltage. What ends up happening is like ions from that water will build up on the surface of the glass, and so the voltage will just continue to sort of climb over time, irrespective of the chemistry, because those things are building up on the surface of the glass. And so you then have to, what you end up doing is you can't like clean it off or anything like that. It just sort of builds up there. And so what you end up doing is you end up going into a standard where you're like, okay, I know for sure this pH is 7. And so what you're really doing is you're just resetting the scale, where like when you first get the probe, a certain voltage translates to a certain pH concentration. And then what ends up happening is as that voltage starts to build up on the glass, your voltage differential there, like the voltage you're measuring, starts to get higher, which would translate to either, I'm not 100% sure, either higher or lower pH. And it will same goes for ORP. What ends up happening is you basically have to go in periodically and just say, hey, this voltage no longer translates to a 7 pH, it now translates to like a 6.8, and this new voltage is 7. And so you have to calibrate it at a couple of points, and then you graph the line where you can now say, okay, this voltage translates to this specific chemistry. And so you have to check that pretty regularly. It doesn't get better over time. And so you're just constantly maintaining it. And then at some point you start to kind of lose confidence.
Yeah, entirely. I think that could actually be an entire kind of explanatory video in itself. We might want to peel that one off as well.
That'll be a better one for Dan, our chemical
Last
engineer, to talk through. He knows a lot about that.
That's true. Yeah, actually he's gonna be the next one on the Sutro Team Spotlight. So we'll definitely zoom into that. Last question, actually, you had mentioned in the beginning that you've also, obviously learned a ton in the 7-8 years that you've been with Sutro. For all the kind of like budding engineering students out there, right? People that are getting into their career, do you just have like a few minutes, like point of advice, or kind of how they could learn, or any sort of like tips or tricks that you've learned as an engineer that you look at other engineers out there that are up and coming in the field?
Sure. Yeah. I mean, some of the advice that I would give is as much hands-on stuff as you can do as possible will really help you out. So if you're like in, studying engineering in college or something like that, join some clubs that are building stuff, doing stuff, take on some projects. It'll help your portfolio for when you get out of school. That's also pretty useful. But also just it'll build your experience. Also working with other people on your engineering team who might know something that you don't, and vice versa, is super helpful, because by the time you're done with that project, you'll both kind of know a lot of the things that you didn't before. So that's super, super useful. And besides that, one hobby, if you can afford it, because when you first start, it's probably somewhat destructive. You get better over time. Would be, if you got like old electronics, old tools, products, what have you, and like they're not working anymore, tear them apart. Like look inside and see how stuff is made, because a bunch of engineers worked on that thing to design it, make optimizations, whether it's, and you'll pick up over time, some of those optimizations are for performance, some of them are for cost. And that's like part of the nuance of engineering as well, is that, not everything that you're designing, you're necessarily always designing to be like the best and greatest at doing a certain thing. Sometimes you just want to enable someone to do a thing or have a tool that they can afford. If the world's greatest drill is like $100,000, I can't afford it to drill a perfect hole. But you know what? There might be a drill for $20 that makes not as great of a hole or as accurate of one, but I can afford it and I can actually use it, right? So there's, I think tearing down products like that will help you like learn the different manufacturing processes, how stuff gets made. You can kind of learn a bit about what sort of like decisions people are making, especially if you can tear down the same type of thing from like multiple like companies, where like I said, like a drill, like tear down like a really expensive drill and a really cheap one, and like see what the differences are. Like, oh, they picked a different motor, like this one's really loud, this one's really quiet, but this one costs 5 times as much, and like, is that worth it? That's for somebody to decide. And then like look at how they're molding parts. You can learn a lot about that. There's a ton of really good like YouTube channels also of folks that do this sort of thing and have like pretty solid engineering experience that will also talk through like, hey, as they're tearing this thing down, like, oh, they chose to do this because X, Y, and Z is a cheaper material, or this is a cheaper process to do it, and like maybe not as accurate, but you can crank out a whole lot more of them and like get them into more people's hands. So yeah, I would say build a bunch of things, tear down stuff that other people have built, and then check out YouTube and talk to people, hear from other people that might tell you stuff that you don't know. And like I said, keep building up that toolbox that you can dig into whenever a new challenge presents itself in whatever work you're doing.
That's awesome. Cool. Great feedback. Awesome. So that'll conclude our Sutro Team Spotlight. Again, today we had Alex Valeyev, who's our mechanical engineer at Sutro. If you don't have a Sutro out there, go to mysutro.com and get one today. And we'll be launching a few more of these. So this is number one. Let's see how they evolve over time. Thank you all for listening, and hope you all have a great weekend, a great week, a great year from whatever time you're listening in the future. Bye.